Let's wait for a couple more minutes. Oh, no, sir, that is, you're defeating us. Yeah, I do. I do. Yeah, I think so. The problem with whoever asks questions will get some kind of use.
Because I'm not. Because I'm not.
You like to speak for a while.
And then.
Yeah, that's all. Yeah, there's some announcements, right? Okay. So this is a section of the workshop, and the last one is Rohit from AMD. So we'll be talking about pair scheduling of indivisible chores. All right, can everybody? Thank you so much. Can everyone hear me okay at the back? Yes? Okay, wonderful. So thank you for sticking around. Really appreciate you being here. I'm going to start with a few acknowledgements. So first of all, thank you, Shweta, for the introduction. Thanks to Omar and Leila for putting together a wonderful workshop program. It's been a lot of fun listening to the talks and interacting with many of you. And thanks to the local organizers for incredible arrangements. I just want to echo the sentiments that have been shared on this stage and in the previous talks, because it's been fantastic. It's been a real pleasure attending this event. Okay, so my name is Rohit. I work in IT Delhi, and I'll be talking about a problem of first scheduling of indivisible chores. Very briefly, it is going to be one of the standard fair division problems with a couple of twists. The first twist is actually a twist that we have seen in the previous talk, which is that although much of the traditional fair division picture focuses on desirable resources or goods, in this talk, we look at undesirable resources of chores, and Vaish already gave us some excellent results on chores, and we see some more here. Bigger interest, though, is going to be the presence of constraints in the fair division model. Okay, so typically in fair division, we imagine that any good can be, or any chore that can be assigned to any agent. There's no sort of infeasibility in assigning any objects to any agents, but in this talk, you'll see that there are some inherent conflict constraints. And those constraints will force us to rethink what are the relevant solution concepts for the problem, determine what the relevant algorithms and existence results for this problem. Okay, so that's sort of the one sentence pitch for what we're going to see. It's a fair division problem with conflict constraints. Okay, all right.
is based on joint work with a bunch of excellent collaborators. We have Sarfaraz Iqbal from IT Bombay. He's in attendance here. Yatharth was an undergrad at IT Delhi. Now he is to the industry. As well as I have a bunch of excellent faculty colleagues, Vaish and Raghuvan from TFR and Rohit and Sarfaraz from IT Bombay. And Sarfaraz is here to answer all your difficult questions. Okay. So here's a very basic cartoon representation of the model that we're going to consider. So we're going to imagine that the resources that we have are some jobs or tasks that arrive over time. Okay, so you see a bunch of gray intervals. Every interval has some start time, some end time. Okay, and there can be possible overlaps among these intervals. We want to assign these resources or jobs or tasks or chores, whatever you want to call them, among the agents. And one of the constraints that the agents face is that they cannot multitask. Okay, so any agent at any point of time can do at most one job. Okay, which means that if you have these three intervals along this dotted vertical line, any agent can get at most one of these jobs. They cannot get two or more of these. Okay, so that's a conflict constraint, which we're going to look at in this model. Okay, so constraints of this form are very naturally captured via graph representation. So imagine on the left you have a bunch of tasks called A, B, C, and D spread out over time. You can imagine every task as a vertex. So we have these four vertices A, B, C, and D. And between any two vertices, you add an edge if the corresponding tasks overlap in time. Okay, so you see that A and B have an overlap. That's why the vertices A and B have an edge between them, and so on. So such a graph is called the conflict graph of the underlying intervals instance. And the class of all such graphs that can be generated from some interval instance, these are called interval graphs. Okay, maybe you've heard this term before. If not, then hopefully this is something new and interesting for you. So this is the class of graphs that will be interesting to us. Okay, we are going to be thinking about allocating jobs, which are modeled as vertices of interval graphs. Okay, and the edges are going to capture the conflict constraints among these chores. Okay? If you have any questions at any point, please feel free to ask. I don't want to defer questions at the very end. I'm very happy to have a discussion throughout the talk. So let me very briefly give you sort of a somewhat more specific model. I'll be relaxed on notation because I know that this is the last talk and people want to see pictures more than letters. So we're going to have indivisible or discrete chores. Okay? So chore is something that we point them. Agents. Okay, so we'll get these n chores among these n agents. Because these are chores, these are undesirable. We have positive value for these chores. So for any chore C, I'll assume that the value Vi of C is less than or equal to 0. The other assumption, and this is not actually necessary for the results, but for the purpose of this talk, let's assume that whenever I give you a set X of the chores, the value for that set X is additive, meaning the value for X is the sum of values of the individual chores in that set X. Okay, I think we have seen this assumption a few times by now. If there are any questions, please ask. All right. Sorry? Yes, it's an English and given my limited PowerPoint skills. Sorry, yeah. So X denotes the bundle of agent. Yeah, exactly. Yeah, thanks. So X is like a tuple, X1, X2, and so on, the bundles of the individual agents. Right, thanks. Okay. So we want to allocate these chores among the agents. So what we're looking for is an allocation because it's a problem that involves a time component. I'm going to call it a schedule. So what is good schedule, right? Suppose we are given an instance of the form as shown here. So so we have these four intervals A, B, C, and D. Okay, and as before, they are captured by a conflict graph. So again, just to remind you, the edges denote conflicts among the intervals. And let's say we're going to assign these jobs among, let's say, two agents. Okay. So let's say I give the job B to the red agent. Okay, that's fine, no problem with that. Because we have conflict constraints around value, that means that we cannot assign A or C to the red agent anymore. So I have sort of five deadlines now by giving B to the red agent. Okay. I can happily assign C to another agent, so the green agent. That's perfectly fine. Okay. You cannot assign A or B to the green agent, again because of conflict constraints. I can assign B to the red agent because there is no edge between B and B. So these are conflict-free items. But example of a schedule that is going to be possible in our model because you don't have chores assigned to an agent, but you have an edge between some pair of chores. Okay, so that's what I'm going to call a feasible schedule. Everyone happy with that? Okay, and note that in a feasible schedule, you can be in a situation where something may not be assigned. Right, so you see that chore A, it can either go to red or to green, it just stays unassigned. Yeah? All right. So we have defined what an allocation or a schedule is. We now want to define what a fair schedule is, because that's something that we would eventually care about. So one word that we have heard a lot on the stage is envy. Okay, envy just means that I like what you have more than what I have, and you don't want envy, right? You want enviness. Unfortunately, enviness is not always possible to achieve. We have seen examples where you have, let's say, one item and two agents, and in case of chores, whoever gets the chore is envious. In case of goods, if someone else gets the good, then it goes towards that agent. In any case, with one item and two agents, exact enviness is impossible. That motivates the consideration of approximate enviness reference, and we have seen a bunch of approximations in this program already. I guess the crowd favorite would be enviness up to any chore or EX. Which says that you look at any pair of agents, I and K, it should be possible to okay, maybe I and these K, but no matter which chore you hypothetically remove from I's body, it goes away. Okay. So for all I and K and every single chore in Xi, if you drop C from Xi, then I does not envy K anymore. Okay, and again, this drop is a hypothetical drop. You don't actually throw away anything. Okay, this is just a thought experiment. So this is EFX. There is a more famous but weaker cousin of EFX, which is EF1, which looks almost like EFX, with the only change being in the quantifier. So instead of allowing the removal of every chore, you just ask, okay, can I drop some chore in my bundle so that my NV agent K goes away? Okay, so very similar notions. It's just that one is for every, the other one is for some. The first lessons that we think about. You able to notice that in the absence of any other visible outcome, these are very easy to achieve, which is the same thing, right? You just leave everything on the table. Everyone has an empty bundle. It's perfectly empty, right? But that's not how you should solve life's problems. Okay, so we're going to demand some sort of efficiency in the problem in addition to fairness. Okay? And we look at a couple of efficiency notions. The more important one for us would be something called maximality. So recall that we saw a picture where we had to leave something unassigned, right, under a feasible schedule. So leaving stuff unassigned is kind of something that we have to live with. Whatever we leave unassigned, we want to have a good justification for it. Okay? So maximality kind of captures that idea. It says that, okay, it's okay to leave stuff unassigned. However, it should be the case that you take something unassigned, give it to some agent, it does not create a conflict. Okay? So the reason an item is unassigned, it must be because no matter who gets this item, it's going to create a conflict for that agent. Okay, that's why this schedule, the current schedule is maximal in certain sense. Okay, so for example, here are two schedules in the same graph. The one on the left is maximal because the green chore go to either red or green. Okay? So its state of being unassigned is justified, whereas in the right side schedule, you cannot justify leaving the rightmost gray chore unassigned because you can easily give it to the red agent without creating a conflict. That's why there is non-maximal. Okay. Any questions about maximality? So this is kind of a bare minimum efficiency guarantee that you might want from your schedule. A stronger efficiency guarantee, which is something we've heard about before, called point optimality. So because we're dealing with chores, I'm going to ask that for a schedule to be point optimal, it should be first of all maximal, and second of all, it should not be Pareto dominated by another maximal schedule. Okay, so I'm asking for Pareto domination by a specific type of schedule, not an arbitrary schedule, because if I allow for domination by arbitrary schedules, then the empty schedule, where everyone gets an empty bundle, that's going to dominate the given schedule, right? So I don't find these vacuous dominations. That's why I'm saying that I won't allow dominations by reasonable schedule, when one notion of modeling reasonableness is maximality. Okay, so you can see Pareto optimality is demanding something over and above maximality. Okay, so it's a stronger efficiency guarantee. Right. So we have defined two illustrations so far, EFX and EF1. EFX is obviously stronger than EF1. And we have defined two efficiency notions, Pareto optimality and maximality, and Pareto optimal is stronger. Okay. So my job is to understand what combinations of these fairness and efficiency criteria are achievable, which means that no matter what kind of instance we are given, we should always be able to achieve that combination of fairness and efficiency. So that's the existence question. And the other sort of complementary question would be, well, can we have algorithms for finding this kind of allocation of schedules? Okay, so we're going to think about two things: existence questions and algorithmic questions. Okay, so let's start to investigate what combinations of fairness and efficiency can be achieved. Of course, it's good to be greedy, right? You take the strongest fairness notion and the strongest efficiency notion. Ask yourself, well, can I achieve that? Right? Wouldn't it be nice if EFX and Pareto optimal schedules always existed? Okay, so I'm going to give you a bunch of bad news in pieces for this talk. The first piece of bad news is that an EFX and maximal schedule, unfortunately, does not always exist. Okay, which in turn, as you can see, implies that EFX and Pareto optimal are also incompatible. Okay, so let's see why that is. So this is going to be a counterexample when the conflict is just a graph. Okay, when you only have agents, and when those agents have identical valuations. Okay, so even in a super restricted setting, you can show that EFX and maximal are incompatible, which means it's a very strong incompatibility. Okay, so with that, on this instance, EFX and maximal are incompatible. So first observation is that you look at the extreme -4 value chore. I think that in any maximal schedule, that chore must not be unassigned. It must go to one or the other agent. Okay, what is that? If you leave the -4 chore unassigned, and let's say the neighboring -1 is going to red, you can happily give the -4 to green. Right? And if no one is getting the neighboring -1, then it will give -4 to some agent. So there is no reason for you to leave -4 unassigned. Okay. So let's say -4 goes to the red agent. Right? Okay. Now, because that I also want EFX in my final schedule, which says that no matter which one you won't eliminate the other guy. Right? If I'm the red agent and you're going to give me a -4 value chore, I really cannot afford to have any other chore in my bundle. Right? Because that would definitely violate EFX. So this is it for the red agent. Red agent should not be given any other chore. Any chores that you assign from this point onwards must go to the red agent. Right? So these are three unassigned chores. Now you can either give it the middle -1 chore to the other agent, the extreme -1 chores to the other agent. That's sort of the only single thing you can do. Okay. You cannot give the middle agent the middle chose the no agent because then you have to give the other extreme to red, and that's a bad idea. So the only thing you can do is to give most chose from that. Sorry, my pointer does not work, otherwise I would have anyway. So you must give this and that chore to the second agent, the blue agent. Okay? All right. So now what's the problem with this? It's not possible because there's a gap between those two blue chores. That means the red agent must be given that chore and the backward value effects. Right? So you cannot have effects and maximality even on the super simple instance, even with two agents and even with identity valuations. Okay? All right. Yes.
Maximality to maximal among the effects?
Maximal among effects. We could, but then you have to like justify something on the sign. Right? It's sort of theoretically interesting, but maybe economically not as well motivated. Yeah, but I guess it's still well defined. We didn't study that problem. Any other questions?
Sure. Example also forbid any approximations of EFX or maximal.
Yes. Yeah, that's not too hard to see. Yeah, you can soup up this example to rule out approximations also. Yeah. Any other questions? Okay. All right. Okay. So EFX and maximal don't go well together. Too bad. So our only hope for getting positive existence results is to think about EF1. Yeah. Okay. Unfortunately, if you insist on EF1, then it's impossible to achieve current optimality alongside it. Okay. Again, it's going to be a very simple example. Once again on a path graph, once again for two agents, and once again with identity valuations. Okay, so again, it's a very strong incompatibility. Let's see why. So, say we have these 5 chores on a path. You see that there are 2 heavy chores, there are 2 negative chores in the middle. Actually, if you give one of these chores to a schedule, you can see that such a schedule can be later improved some other schedule where none of the heavy chores is assigned. Okay, so if any schedule gives negative 10 to one of the agents, let's say the red agent, then such a schedule is dominated by a schedule of this form, where you avoid assigning only the high value chores and only assign sort of these odd indexed chores. Okay, the negative 1, negative 2s. Okay, this is not too hard. I'm not going to the formula, but it shouldn't be too hard to see. So really the only non-related schedules in our problem are the one shown here and the color swapped version of the schedule where red gets the middle one and blue gets the extreme ones. However, there is a problem with this dominating schedule, which is that it is not EF1. Right? If I'm red, then no matter which chore I drop from my bundle, I still end up in the agent. Okay, so if you want predictability, there's no way you can have EF1. All right. Okay. So I want to add a remark at this point, because I think this example sort of sheds light on why the constrained model is really much harder than the unconstrained model. So the unconstrained fair division model is where any item can be given to any agent, whereas the constrained model is the one that we're looking at here, where there are pairwise conflict constraints. So in the unconstrained model, if you have identical valuations, it's fairly easy to see that every allocation or every schedule is Pareto-optimal. Okay? The reason is that every item contributes equally to the social welfare, which is the sum of utilities of the agents. Okay? So in the unconstrained model, Pareto-optimality is super easy when the values are identical. However, in the constrained model, even with identical valuations, Pareto-optimality is kind of tricky. Okay, it certainly does not do well with EF1. All right. Okay. So unfortunately, EF1 and Pareto-optimal are also incompatible. So now we are really sort of in a tight space where we only hope for some positive results is EF1 and maximality. Okay. All right. So let's explore what can we say about EF1 and maximality. So here's the EF1, and if you're somewhat familiar with the fair division literature, Your overall response is to think about the round robin algorithm, because it's a different essential algorithm to find EF1 allocations, at least in the additive valuations. So if you haven't heard of round robin, let me just take a few seconds to remind you what it does. So this is a sequential algorithm. Okay, it gives regions, let's say A1, A2, A1, right? And in each round, it sort of cycles through that order. In each round, an agent gets a turn to pick an item that it likes the most. What items are left? Okay, so in the first round, let's say A1 goes first. It picks its favorite item, right? And then goes to another queue. Then agent looks at whatever is remaining, picks its favorite item, goes to another queue, and so on. Okay, and once you have this sort of exhausted regions, you cycle back in this order again in the second round, and the third round, and so on until you have exhausted all the items. Okay, and then in the last round, some agents might get an item, some others might not. That's just life. Okay, so this is the round robin algorithm. When you have no constraints, when you're in the unconstrained model, it's not that hard to see that round robin is a given EF1 allocation. Okay, let me do a very quick picture because this picture is going to be relevant later on in a few minutes. So here's why round robin is EF1. Because the EF1 is a pairwise guarantee. So fix a pair of agents, let's say red and blue, and let's think of the NV of the red agent towards the blue agent. Now, let's first consider the case where red is ahead of blue in the order. Okay, so in each round, red gets to pick an item before blue does. Okay, so if the execution of round robin is what you are seeing on the slide, it might be possible that in the final round, say red gets an extra chore, whereas blue doesn't. That's possible, right? For all we know. However, if you hypothetically drop that last round chore from red's bundle, then item for item, red prefers its own bundle, blue's bundle, right? And because of additivity, it prefers its own over that of blue. Okay? So after the removal of the chore C, red does not envy blue. Okay. So this is for the case when red precedes blue. What happens in the other case where blue is ahead of red? Very similar argument, right? So let's say, to give essentially extra advantage, let's say red this time does get, like both agents get some sort in the last round. Once again, you can see that whatever item red picks in round K, if V2 prefers an item, or blue picks in the next K plus 1th round, right? Because both items are on the table. So after the removal of the last item in red C, again, item for item manner, red likes its own value, a subset of these values, right? And if you are chose, you are going to be chose to get out of this window, and the witness relation will not change. Okay? So even in this case, you can see that round robin is EF1. Okay? So this is kind of a sort of a perfect picture for why round robin gives you EF1. Just keep this sort of array-based picture in mind. We'll come back to it later. Okay. So another bad news that I'm going to give you in this talk is that this very nice algorithm, which works beautifully well in the unconstrained model, it fails miserably in the constrained model. Okay, so it fails to give you EF1. Again, even when you have a path graph, even when you have two agents, and even when they're identical. Okay, so let's see why. Let's say the chores are lined up in the order that was shown. If you have a red agent and you get to go first, obviously you jump on the chore that is valued at 0, right? Then the blue colored agent would go, it picks the -1 value chore. When red goes, picks the -2. And now it's blue's turn. However, we would love to get the 3 chore, but it can't because of the conflict constraint. So it has to settle for a worse chore, which in this case is a -7. Okay, and red will take advantage of that on its turn, because it can happily take -3. Yeah, so it's going to do that just to sort of rub it in, and then the blue agent will go again and it will again take a very bad chore. Okay, so as you can see, because of the conflict constraints, we can do a build-up of AMD as the algorithm goes along. So for the time, we will do so much that we will sort of satisfy the EF1 guarantee. Okay, all right. So even if the blue agent drops this worst chore from its bundle, it would still envy the red agent. That's why this allocation is not EF1. There's another very sort of relevant algorithm for finding PF1 equations in the unconstrained model, which is a variant of the MD cycle algorithm. It's called the top coding MD cycle algorithm. Unfortunately, that algorithm also fails to find EF1 schedules when you have conflicts. And for a very similar reason, that you will be able to certain items to certain agents, but you cannot because of conflicts. Okay, so that again builds up envy and the algorithm fails. Okay, all right. So we only have basically one big run, which was round robin, and it does not work, which means we sort of need to rethink what kind of algorithms we can come up with in the conflict model. And to be results. So the first result that I want to present to you is that when and when the conflict graph is a path graph, and EF1 and maximal schedule always exists. Okay. So this might seem like a very restrictive result, right? Just two agents, just a path graph. What is the big deal? The reason is that the reason I found this result interesting is that all the counter examples that we saw before, they also path graphs, also two agents, and even for identical valuations, right? So getting some kind of positive results, even in that very restricted model, is somewhat non-trivial. Okay, I think it's somewhat interesting. So this result is sort of making some progress towards that goal. There are a few positive signals to this result. This result actually does not need additive evaluations. Okay, so as long as you just have the monotonicity structure, the result goes through. Okay. This result also is not just an existential result, it comes with a nice polynomial time argument. Okay, so this is actually an algorithm, so you can find an EF1 and maximal schedule in polynomial time. And in fact, the argument, the proof idea that I'm going to show you in just a minute, you can use that to extend this result to general interval graphs, slight loss in the fairness approximation. Okay, so you can definitely show that you can get MD2 shows or EF2 for general interval graphs. Okay. Yes.
Generalization, the number of agents still remains.
Yes, everything is for two agents. It's just that I replace paths with interval. Yeah. And again, you continue to have monotone and continue to have polytime even in that case. Yeah. Any other questions about this result? So I'll give you a sort of a high level proof sketch of this in just a minute. Okay. So the second result I want to present is for a general number of agents, not just two, because two feels restrictive. However, in this case, we are going to make some stronger assumptions on the problem. Okay, so when you have an arbitrary number of agents, however, if they have identical valuations and the conflict graph is still a path, you can show that an EF1 and maximal schedule always exists. Okay, so unlike the result at the top, which did not require identical valuations, the bottom result does require identical valuations. So agents are copies of each other. There are a few depressing footnotes to this result. And the first depressing footnote is that, unfortunately, we don't know how to extend this result to general monotone valuation. So all we can show is that it only applies to additive valuations. Okay, so it's not as general as the top result. The bigger worry is that this is essentially a largely non-algorithmic result. It's an existential result. So it does not come with an efficient procedure for finding such a schedule. Okay. So there's a sort of a bit of a contrast in terms of generality and computation between these two results. Okay. So these are the things that we are going to see in the next few minutes. Okay. So let's go. Let's look at for the first result. So because that we are trying to prove for two agents on EF1 and maximal schedule always exists. Okay. And this proof is going to be something called what we call a color switching technique, which I hope we'll find interesting. It's a neat idea. So let's say we're doing a path graph like this, and we have two agents, and we'll find an EF1 and maximal schedule. The first step that I'm going to do in this algorithm is I'm going to start with an alternate coloring. Sure, so I'll do red, blue, red, blue, red, blue, and so on. Okay. And I'll call that schedule X1. Now, as you can see, this is a maximal schedule. Everything is assigned, but it may not be EF1. Right? Agents could be highly envious of each other because I really didn't ask them for their preferences. I just colored things that I liked. Okay. Anyway, so let's imagine a color flipped version of this schedule, which is colored blue, red, blue, red, blue, red. Okay. I'm going to call it X6. You'll see why 6 in just a second. One thing to note between the starting schedule and this target schedule X6 is that the bundles of the two agents have switched. Okay. So let's say I'm the red agent and say I was envious of the blue agent under X1. Under X6, I have gotten the bundle of blue agent, which means my envy towards blue has gone away. Right? So if I start from X1, and let's say I construct for you a sequence of schedules, and I end up with X6, then that means that at some point in the trajectory, my envy would switch directions. Yeah? Okay, so just be on the lookout for where that switch happens, and really that's going to be the point of interest for us. Okay. So what does the algorithm do? It starts with X1. It's going to make some local tweaks to the current schedule each time. It's going to appear a new schedule. And then a sequence of local tweaks, it will eventually take us to the target schedule, which is the color flipped version. Okay. How does that work? Okay. So let's see, let's look at the first two chores, the red and the blue chore. Okay. We're going to turn this red into eventually, and this blue to red. That's our goal. Okay. So we're going to make some progress towards that goal. By making the first chore blue, the second chore unassigned, and leaving everything after that, the whole tail untouched. Okay. So this is one tweak that we're going to make on top of X1. And this step preserves maximality. Right? So the only unassigned chore, the blue one, it cannot be given to either of them because it's sandwiched with blue. This is a maximal schedule. Again, I don't know whether it is EF1 or not. Right? Whenever it's 74, you know. Okay. Let's keep going. Okay. So we have fixed the first chore. Now let's look at the next two chores. Okay, we're again going to fix one of the chores. So let's turn the second chore. The third chore we can assign, and then we not touch the rest of the tail. Okay. Okay. So I hope everyone sees where this is going. Okay, we just made these sort of small tweaks and keep going this way, and eventually what we end up with is the color flipped version of the initial schedule. Okay. So why is all of this interesting? As I mentioned before, at some point in this trajectory, the envy must switch. Right? So if I'm the red agent, at some point I'll stop envying the blue agent. Okay. At every step of the way, I'm maintaining an invariant maximality. So every single step, every single schedule in between X1 and X6 is definitely to be maximal by construction. Okay. So everything is maintained maximality, and at some point, there is switch from envy. Okay. And really, that is the place where we can identify EF1 schedule. Right? I'm not going to prove this formally, but really, because just one chore on the bundle, you envy switches, and that's hopefully you can see that gives you the EF1 property. Okay, so I'm not going to define it, but this is something that you can prove to yourself over the coffee break. Any questions about this approach? Yeah. Yeah, so let's understand what we mean by work. So if by work you mean, let's say you can get something weaker than EF1, let's say EF2, then yes, it goes through for interval graphs. If you insist on EF1, then I'm not sure how far beyond path graphs we can go at this point. Yeah. Yeah.
It feels like you can generalize this argument for any.
Well, with n agents, the thing is, I don't have sort of a very defined sort of switching strategy, right? Because if you have three agents, we're going to switch the bundles, and it's just cyclic swap rather than a complete sort of change. So I don't know how to identify these switchover points. It becomes slightly tricky. Any other questions? Okay. This is sort of the rough idea of finding EF1 and maximal for path graphs. Let me very quickly sketch an argument for the other result, which applies to any number of agents. as long as they're identical. Okay. All right. So I told you that this is a largely non-algorithmic result, and that's a sign that I'm probably using some heavy hammer, right? Some kind of fixed point theorem or such. And indeed I am. So this heavy hammer is called the cycle plus triangles theorem. This was actually based on a conjecture of Paul Vaish, which was proven by these two people, Fleischer and Stieglitz in 1992. So what is this theorem? So this theorem says that, okay, imagine a graph whose vertex set is a bunch of triangles, like so, okay, so a bunch of disjoint triangles, and whose edge set consists of a disjoint of two things. One is the edges of the triangles, the dark edges that you see, and the other thing is a Hamiltonian cycle. So it's a cycle that touches every vertex of the graph. Okay, so the theorem asks us to imagine a graph in which you can decompose the edges into triangle edges and Ham cycle edges. Okay, these are the only graphs to which this theorem applies. So whenever you have such a graph, the theorem says that such a graph is three colorable. Okay, that means a proper coloring with three colors. For example, you can color every triangle red, blue, and green, such that there is no edge between vertices of the same color. Okay, it's a proper coloring. So any such graph always admits a three coloring. Okay. All right. So this theorem is not just
So the edges needs to be, the Hamiltonian cycles need to be disjoint, or the edges should just appear either as a Hamiltonian or as a triangle edge.
the set of edges consists of triangle edges and Ham cycle edges.
Yes.
So it's a big one of the two.
Thank you.
Any questions about the statement of the theorem? Okay. So just one remark about this theorem. This kind of theorem, you might be wondering why triangles, right? What if I have sort of larger components? So even if you have, let's say, a K4, a clique of size 4, a clique of size 5 instead of triangle, and so on. For all those things, you can make such a statement, right? So if you have a sort of a K-size clique and a disjoint property that you have a clique edges and a Ham cycle, such a graph is K colorable. So this theorem generalizes to sort of arbitrary K. Okay. However, we don't have algorithms for finding such a coloring. So this is a purely existential result, as far as I can tell.
Because of the decomposition property, it's not efficiently decomposable.
Yeah, so to my knowledge, the proof of this result actually uses the common denomination results of Alan and Darcy, fairly sophisticated techniques. I think I've seen on Mail that if you have disjoint union of K4s, then you can compute the four elements, the algorithmic versions of the local lemma. But for all other cases, as far as I know, there is no efficient algorithm. So that's why I say it's largely not algorithmic. Okay, so I'll just keep this as an existential black box for our purpose. Okay. Okay. So let's just sort of keep this picture in mind that such graphs are three colorable. And let me tell you how any of this can give us fair and efficient schedules. Okay. All right. Okay. So remember, what we are trying to prove is that we are given a graph, okay, where you have n number of agents, arbitrary number of agents with identical values. So I can happily put numbers on the vertices with the comfort that every agent values the leftmost row as -9, the next to it at -6, and so on. Okay, because these are identical values. And I want to find an EFI maximal schedule in this instance. Okay, how do we do it? So what we will do is we will identify, let's say we're doing three agents, because I'm doing a triangle result, so why not? Let's identify the three worst chores on this path. Okay? Because the values are identical, everyone thinks that the same set, the same chores are the worst chores. Okay? So the three worst chores are -9, -8, and -7. Let me put them together and put edges in between them. Okay? All right. Next, I'll identify the next three worst chores, which is -6, -5, and -4. Again, I'll create a triangle out of them and keep going. Okay, so you sort of identify triangles of the worst three chores, and you sort of keep creating these triangles, and hopefully at some point we'll exhaust everything. Okay, so for this example, I'm assuming it's a multiple of 3. That's really without loss of generality. Okay. Okay. So I gave you the cycle plus triangles theorem. I've given you the triangles. We're still missing a cycle, right? Where did we get that cycle from? Well, we really get that cycle from the path that's shown above in the slide. Okay. So for every edge of the path, so you have the -9, -6 edge, -6, -3 edge, and so on, we're going to plot that edge in this new graph that we're developing. Okay. So I'm going to add an edge between the vertex representing -9 and okay, so sorry, I'm jumping ahead. So the first edge that I need to add is an edge between the most extreme shores, the left and right, -9 and -2. Okay, because I want to sort of complete a cycle, I only have a path. Okay. Once I've done that, then I'll add edges between the neighboring shores on the path. So -9 to -6, then -6 to -3, and so on. Okay. So I'll sort of scan through the path and keep adding those edges. Okay. And happily for us, that gives us a ham cycle. And the cycle this triangle theorem, such a graph admits a free coloring. Get them. I think this. However, I've conveniently chosen an example where I don't have to do this. We have a construction where you can add gadgets. So this whole thing still applies to simple graphs. So this is not a non-issue. Yeah. Still go through. Yeah, yeah.
If it's not a multiple of 3, are you going to just?
Conflicts, that's still fine. Quick.
Here doesn't for not triangle, but for edges. So for K2 or something like that, you can get non.
Yeah, that's only triangles and above. Exactly. Yeah, it doesn't apply to K2, and I think the fractional and civics paper has an example of that. Yeah, good point. Any other questions? Okay, but I mean, I know to how to do it, so that's the non-issue. Yes. So sorry.
If the path had -9 and -8.
Exactly. So that's what Jyoti was asking. So after this example conveniently, even if you have a -9, -8 edge, it is possible to add sort of a constant size gadget and sort of complete the cycle that way. I'm not showing that because it's just a detail. Yeah. Yeah. Any other questions?
Question on Jatin and Sanjay, I'm not sure.
You see, at the edge of the cycle, we jump between different triangles. Right? Right? I've conveniently chosen an example, but that's a non-issue because we have entire gadgets. I'm not showing it here. Okay. All right. So, right? We developed this new graph, which was a bunch of triangles cycle around it. Right? Cycle this triangle theorem is that there is a 3 coloring for this graph. Right? So imagine similarly to 3 coloring in your real path graph. Okay, so we just sort of see the allocation suggested by the 3 coloring in our equation problem instance. What does that mean? It means that if you add the red version, then I'm getting one shore from each component. Right? So if I compare my red bundle against, say, a blue bundle, then I can happily draw my shore in the worst component, right? And then item for item, I prefer my bundle over yours. Right? Because that's how I design these components, right? The 3 worst shores are one component, the next year another component, and so on. So once I drop my -9, then again, item for item, I won't envy. Okay, so it's exactly the round robin argument that we saw before. Okay? Okay. Cool. Any questions about what is the offense? I'm not, again, suppressing the details, but really that's the argument. Cool. Okay, so let me just finish with some open problems. So bunch of future directions that I'm quite excited about. Firstly, just sort of following from the results I showed, we are really lacking algorithmic results in this study, right? So I don't know of algorithms for finding an EF1 and maximal schedule for a general number of agents, right? So we saw everything for 2 agents, but for n agents, it was a plain existential argument. Then we turned that into an algorithm, right? And a good starting point would be you just think about path graphs and you just think about identical valuations, right? Setup, can we still get some nice algorithmic results? I think that's a nice direction to follow. It's mostly obsessed with the NB freeness and its relaxations in the stock. host of famous persons are there, the personality, maximum share, equitability, enterprise share. There's many things that one can think about. And I think all of those apply to this model. I only present the results for chores. Some of these results actually go through even for goods, but I think such studying goods and its resources more systematically in the conflict model would be interesting. And I think a very interesting that comes to interval graphs. Right? So I used interval as a motivation, but really from that point onwards, I just worked with graphs and colorings. Right? And the problem of finding EFR and maximal schedules is well defined for general graphs, even non-interval graphs. So what can we say, for example, for two agents and non-interval graphs? Do EFR and maximal schedules exist or do not? I think that's an interesting question to study. Okay, all right. So that's all I want to say. Thank you very much for your time. I'm happy to answer questions.
Questions?
Yeah. 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 So the gadget is just a bunch of three other triangles, such that even if I have this situation where the cycle sort of has a multi-edge situation, right? I don't have to develop the cycle that way. I find the gadget, and everything is it's a simple graph. So these are multi-edges. Although the theorem still holds for multi-graphs, I just wanted to keep it clean. So yeah, it's a technical detail I can tell you about later, but yeah. Rick, yeah.
So I think this goes back to someone else's question as well, but in the two agents algorithm that you showed, it feels like path with one graph, so caterpillar graphs. As long as you have sort of a canonical rendering of edges that covers the whole graph, you are able to do that kind of switching argument. So I would say if there's like, do you know anything about low path width graphs or something like that?
Yeah, I mean, maybe this we haven't thought very seriously about it. Yeah, but what I know is that if you jump directly to interval graphs, then it involves a lot of case analysis and so. So EF2 is sort of clean. EF1 is sort of involves a lot of case analysis, but maybe there are sort of things in between, low path squares, capitals, not something that we have very seriously thought about, but yeah. Sorry, bounded path squares. Right, even two agents, right? Yeah, I think just that would be interesting. We check if the coloring idea sort of goes through for that.
You can keep some information and so on.
Yeah, I'm just a little bit worried about maximality in a clean way. It was very easy to define that local incorporation. For that, I'll have to
talk. We can talk.
Later. Yeah.
Can
So in that argument where you started with one path and you flipped, the other path is completely flipped. And you chose arbitrarily one way to travel, right?
Yes.
There could be many ways.
Possibly. But the idea is to try to switch over point, right? With two agents, it's very natural to think of alternate colorings and switching numbers. As I think Rick was asking before, if you have, or maybe Vaish was asking, like if you have two or more agents, it's not clear what a switch means. You're sort of exchanging complementary bundles.
So even for two agents, just choosing a different way or something give a different.
Yeah, I don't know if other coloring techniques. Yeah, maybe but it was just a proof, right? Definitely not the only way. Maybe there's some other coloring technique out there. Yeah. Everything.
So we've missed if you mention what are the hardness results known in this setting? Are they?
So we have non-existence results. We don't have NP hardness results in the paper. Yeah.
Thank you, Rohit, again.
Thank you very much.
And that brings us to the end of the workshop. So yeah, hand it over to Manu.
Yeah, I'll just say a few things. So first and foremost, obviously a huge round of applause for our local organizers. They've been absolutely amazing, and the student volunteers also, you guys have really done an absolutely fantastic job running around with the mics, telling people to stand in one place and not move around, stuff so that it all comes on YouTube. It's really absolutely excellent.
Several the audience as well. Usually by the end of the last session, people can't wait to get up. Here, people still want to ask questions, can't let the speaker go, even though he went, I think, 10 minutes over time. So, yeah, so thank you all for being here. I'm sticking. Because when we look at people who very clear, we can't pay for your power, you still want to come. And almost everybody said, absolutely, yes. They came, they gave great talks, they Photoshop, they jumped around the place, they increased the level of the of the energy in the place. So thank you to the speakers as well. I guess two final things, like I said, so there will be plan of activity around around theory, social choice, and so on, workshops, schools. If anybody have suggestions on how this can be better organized, longer, shorter, different kinds of talks. For example, here we had some thoughts of having an open problem session, but all the talks present open problems as well, so it wasn't clear if that would be helpful. If you think that might be helpful, please tell us. We can think about that as well. What would you like to see in a similar session or in a similar workshop? So I want to say is that while we were coming, we saw a bunch of children schools around Ahmedabad. I think we have these stalls in which they're showing science demonstrations and puzzles and so on. It would be nice if you could talk to them on the way out. If you know Hindi, it would help a little bit, but I guess the language of puzzle is universal. So even if you don't, that should still work. But thank you once again, and yeah, we'll see you all. We'll see all of you soon.
Last word goes to you.
Last word. No, these are just completely mundane logistics. Of course, I'll echo the thanks to everyone. In fact, go to fsttcs.info/thanks for a more elaborate note on everybody that we do want to thank. But there are some snacks outside, and so please don't miss that. And I suppose you will receive an email with a link to a feedback form. So whenever you have a chance, please share your ideas on how we can do this better. I'm just going to pass it all on to our friends at Bit School. So see you at FST 2025. Thank you so much, everybody. Thank you.